All right, everyone, welcome. In power electronics, pretty much everything boils down to one thing: control. And today we're going to get right into the heart of it. We're talking about one of the most fundamental challenges you'll face as an engineer. How do we pick, and how do we control, the semiconductor switches that make basically everything work? I'm talking about your phone charger, right up to the entire electrical grid.
Okay, so here's the game plan. First, we'll lay out the core problem. Then, we'll dive into what I like to call the 4 philosophies of switching. After that, we'll look at how fast these things can actually go, and finally, we'll pull it all together into a practical way for you to choose the right device for the job. Sound good? Let's jump in.
So, first things first. You've got to understand that at their core, these power semiconductor devices, they're really just incredibly fancy switches. That's it. Their entire job is to turn on and off, over and over. We're talking thousands, sometimes millions of times a second, all to precisely shape and control the flow of electrical power.
And that really brings us to the central question, doesn't it? I mean, in a perfect world, in our textbooks, an ideal switch would have 0 resistance when it's on, infinite resistance when it's off, and it would flip between those states in 0 time, instantly. But we live in the real world. Those don't exist. So the whole key, the secret sauce to controlling real devices, is getting to know their unique quirks and characteristics. Okay, so this leads us perfectly into the 4 main families of control. And I really do like to think of them as different philosophies for how you approach turning these switches on and off. Let's break them down, one by one. First up, we have the thyristor. The best way to think about this one is like a mechanical latch on a gate. You give it a little push, a small pulse of current to its gate terminal, and snap! It swings open and stays open. It's now conducting the main current. But here's the really important part, the catch. You can't push it closed from the side. You can't turn it off from the gate. It's stuck on, or latched, until the main flow of current passing through it stops all by itself. That's why we call it a partially controlled device. All right, so if the thyristor has that one big limitation, this next family of devices is the answer to that problem. We're talking about things like the gate turn-off thyristor, or GTO. It starts out just like a regular thyristor. You turn it on with a positive pulse, but it gives us an escape hatch. We now have a way to force it off. By hitting the gate with a pretty strong negative pulse, we can actively command the switch to turn off. Now that gives us a whole lot more control over what's happening.
Okay, now let's shift gears completely. The bipolar junction transistor, the BJT. This is a totally different way of thinking. This is not a latching device. For a BJT to stay on and conduct current, you have to continuously feed a little bit of current into its base terminal. Think of it like holding down a button. The switch is only on for as long as you're actively holding that button down. Want to turn it off? Simple. Just stop that base current. Take your finger off the button.
And that brings us to our 4th philosophy, which really is the modern approach you'll see everywhere. This is the world of MOSFETs and IGBTs. The big breakthrough here? We're not controlling with current anymore. We're controlling with voltage. You apply a positive voltage to the gate, it turns on. You remove that voltage, bring it back to 0, it turns off. And here's the beautiful part. These devices have an incredibly high input impedance. That's a fancy way of saying it takes practically 0 current to control them. This is what makes them so efficient and allows for the mind-bogglingly fast switching speeds we rely on today. So let's just pause and summarize. We can really split all these devices into 2 big camps, right? On one side, you have the partially controlled latching devices like thyristors and GTOs. You can turn them on, but turning them off is complicated. On the other side, you have the fully controlled devices, your BJTs, MOSFETs, and IGBTs, that you can turn on and off whenever you want. And let me tell you, this distinction, it is absolutely fundamental to how you design a power converter.
Okay, so now we know how to control them. We've got our 4 philosophies. But that's only half the story. The next absolutely critical question is, how fast can they go? Because, and this is a huge takeaway, the switching frequency has a massive, massive impact on the size, the cost, and the efficiency of any power converter you'll ever build. And this table here, this just lays out a classic engineering trade-off. It's something you'll see over and over again. Look at the thyristor. It can handle immense power. We're talking 12 kilovolts, 5 kiloamps. But look at its speed, less than 500 hertz. It's a brute, but it's slow. Now look all the way at the other end, the MOSFET. It's blazing fast, over 100 kilohertz, but its power handling is way, way lower. The takeaway here is simple. In this world, you can't have it all. There's always a trade-off between power and speed.
Seeing it in a table is one thing, but when you visualize it like this, The difference is just staggering. I mean, we are not talking about small incremental improvements here. Look at that jump in speed. It's almost logarithmic as we go from the big, slow thyristors to the zippy little MOSFETs. This right here, this incredible speed is what makes all of our compact, high-frequency gadgets possible. Think about your laptop charger. It wouldn't exist without this.
So, okay, we've got control types and we've got performance data, speed versus power. Now for the real question. How do you put all this together to actually choose the right device for a specific job? This, my friends, is where the science of engineering meets the art of design. And the most important thing to get in your head is that there is no single best device. It just doesn't exist. It's all about the application. You know, you wouldn't use a sledgehammer to hang a picture frame, right? And you're definitely not going to use a tiny little MOSFET to run a high-voltage DC transmission line. It is always, always about matching the right tool to the right job. This table gives us a fantastic roadmap, a great starting point. It basically maps out the power landscape. Are you working with huge megawatt-level industrial drives? Yeah, you're probably going to be looking at thyristors, maybe GTOs. What about a medium power application, say the tens to hundreds of kilowatts for an electric vehicle inverter? That is prime IGBT territory. And for all the low power stuff, anything under 10 kilowatts, your phone charger, your computer, the MOSFET is king. So you can really picture this as a spectrum, right? On one extreme end, you've got these massive grid-level applications like HVDC transmission. Here, all you care about is raw power handling. You need a device that can withstand huge voltages and currents. So the slow but incredibly tough thyristor is perfect. Speed just isn't the main concern. Then way over on the other end of the spectrum, you have things like the power supply in your laptop. The goal there is to be as small and efficient as possible, which means you have to switch at incredibly high frequencies. And for that, only a super fast MOSFET will do the job. All right, let's bring this all home. I want to distill everything we've talked about into a simple, repeatable process, a framework that you can literally use for any design you work on, whether it's a lab assignment for this class or your very first project at a new job.
Step 1, you always start with your power and voltage requirements. How much voltage does it need to block? How much current does it need to carry? This is non-negotiable. It's a hard line. Step 2, think about your control needs. Can you get away with a simple latching device, or do you absolutely need full on-off control? And finally, step 3, you evaluate the frequency. How fast does this thing need to switch? If you walk through these 3 steps, in this order, you will almost always land on the right device for your application.
And that's pretty much the grand tour of power device characteristics. But I want to leave you with this thought. The field is never static. It is constantly moving forward. We have new materials, these wide bandgap semiconductors like silicon carbide and gallium nitride, and they are starting to break these classic rules we just talked about. They're promising high power and high frequency in the same device. So the most important thing I want you to take away is to understand these fundamental trade-offs, because if you get that, you'll be able to navigate the field no matter how the technology changes. Always ask what comes next.